This part we will talk about powder density. Okay, so we just talked about particle density, right? Again, very similar, but powder, it's the bulk material, right? So why powder, bulk density is important. Again, I've given one example here. It's very important to know the densities when you're shipping and handling, right? It's an example of filling grains in a large, rail car. It's a truck. Okay. So if you know the bulk density, you can, you'll know how much material you are putting in large container or even small packs, containers, etc. So again, almost very similar to particle density, the bulk density also influences all the flow, disintegration, mechanical properties, shipping efficiency, product, performance, etc. We'll go through some examples. Okay. So when it comes to flowability, we will talk about flowability in the next lecture too. Okay, I'm not sure how many of you heard about this term Hausner ratio. It's developed by Hausner. So from the ratio of tap density and aerated, or rho A is the aerated bulk density or the bulk density, as we simply say. Okay, so based on this relationship between the tap density and the bulk density, he tried to assess the flow behavior of powders. Okay, so again, this is a common, very commonly used by most of the powder industry. It's not a quantitative indicator of flow, but it gives a qualitative indicator of how well the powder might flow. Okay, so using those two values, and this Hausner ratio is also directed to CARS index. Anyone heard about CARS index? No. Yoda. Okay, we'll talk about that too. In the next lecture. So CARS index talks about compressibility. So this Hausner ratio is also directly related to the compressibility of the material. Okay. So if the bulk density and the tap density are almost same, then the compressibility will be low, right? So it's not changing. When you tap, if there is no change in volume, then the bulk density will be very same as tap density, right? But if the material is changing in volume when you tap, if it's reducing in volume, then the tap density will go up, right? So then their compressibility value will also be high. Okay. So many times you might have seen, that's one advantage of filling with gases, right? So it doesn't change volume much. In packs, when they are packing food materials, either it's if it's vacuum packed or if it's packed with gas, then the volume remains constant. At least the consumer will not think that I'm getting reduced quantity of material for the same price, right? So it's very important when you are like shipping, etc. Okay, so if you are filling powders in containers, the volume should remain the same, right? At least for consumer, if they take 2 bottles, the level should be the same, right? So if the tap density is high, if one bottle is going through vibration and shaking process, its volume reduces, right? So the consumer might think, okay, it's not, I'm not getting the value for money, right? So these are, again, important when you are, handling and shipping. Okay. So again, Hausner, we'll talk about this in the flow lecture too, but based on this relationship between tap density and bulk density, he defined a subjective flowability. Okay. So as I said, if the compressibility is low, or if the bulk density and tap density are very close or very similar value, then the Hausner ratio is very low. That indicates the powders will have a better flow behavior. Okay. If it's not compressible, then it might flow very well. Okay, when you are like transporting and handling. But if the tap density is high, if it's changing a lot, then the Hausner ratio value goes up, and that will indicate poor flowability of materials. Right. But again, this is also used for characterizing fluidization of materials. Okay, it also influences. Not sure you would have, we saw a chart in the fluidization chart, right, in one of the lectures before. Anyone remember? It's a Geldart chart that relates density and particle size and their fluidization behavior. No one remember? Anyone remember the Geldart chart from previous lectures? Okay, so I mean, you might remember when you check back. It's a relationship between particle size and the density. Okay, so you might have seen like 2-3 lines inside. So in one part of the section within the graph, that will show good fluidization behavior of powders if their relationship is in that area. If it's very fine powder, it's very difficult to aerate. If it's large size particles, then also it will be very difficult to fluidize. I gave an example of popcorn, right? Popping. So it will sprout then fluidize, right? So same thing, Hausner ratio can indicate the fluidization behavior of these powders too, right? So again, how affects the porosity or mechanical properties? Again, in general, the porosity or the change in values of the property can be directly related to the porosity or void space, change in void space. Okay, so this P can be anything. It's a property at zero porosity, and P will be the actual porosity value. Actual property value that you are measuring. Okay, it could be bulk density, it could be tap density, etc. Can be related using an exponential relationship. Okay, so again, alpha is the fitting constant. Again, F1, F2 are constants that we can derive from those relationship between void space and the change in property value. Okay. So again, one big challenge of using this relationship is extrapolation to zero porosity. So if you extrapolate these values to zero porosity, you get wrong values. So you cannot extrapolate to zero porosity. Okay. Other than that, it gives a reasonable estimation of the change in properties, based on the change in void space. Okay. So when we characterize density, we are characterizing the void space, right? The pore space. That's what we are doing, right? So where and when and how the void spaces are changing and how it's influencing, is that what we characterize in different types of densities, right? Again, as I just said, Sprig's equation, that's the direct exponential relationship. So almost fits well the properties, and as I said, only challenge will be extrapolation to zero porosity, then the values might be wrong. Okay, but other than that, it fits well with most of the properties. Okay, any questions? Okay. So you might be wondering why we are talking about Sprig's equation in bulk density, right?
Sir, what do you mean by extrapolation?
It's the same. You have the values, right? But if you draw the line to zero porosity, this value might not be the actual value. That it's very difficult to measure at zero porosity. But this equation says we can go up to zero porosity. You see, P0 is a property at zero porosity. Is that clear? Yeah. The fitting constants? Yeah, from the fits. You plot it and then fit it. Okay. So again, the intercept is the P0 value. Okay. Oh, Young's modulus, by compression usually. What's usually we measure by uniaxial compression. Uniaxial compression. Yeah. We'll talk about Young's modulus, all those things in the last part of the lecture. Okay, how we characterize Young's modulus.
we will get the young further. And how will we just correlate that to mean porosity? Like for our porosity, we'll get a young further. And how will we correlate this to?
I don't.
We are doing this like UniXAM compression.
Yeah.
Then if we will get the young further,
Mhm.
then we'll get a stress corresponding to strain.
Yeah.
Then we'll correlate.
Yeah.
We'll get the mean porosity from this.
So that's for you are compacting at different forces. So you will compact at different forces, then you get compacts with different porosities. For example, if you're using compacting at 50 megapascals, okay, so your void fraction will be different than when you are compacting at 100 megapascals.
How will you create that? How will you know that for that pressure you will get that porosity?
Or it's by it's not that's by experiment, one thing, okay. So you'll have to compact and then measure the porosity.
First we have to compact this powder after that we measure.
The porosity, yes, yeah. If not, so you know, right, so from the true density and the apparent density, so you can get the pore space, right. So you can use that, we'll do an example too in this, you can get the porosity, bulk porosity of compacts, okay.
We have to check different Pascals. We have to check value of this Young modulus.
Yeah, so Young's modulus, if you change compression, it's stress over strain, right. So yeah, so you'll have to change stress and strain values and then get different porosity. So this, don't go into the graph too much, I'm just showing as an example, okay. We'll talk about these properties in the last part of the lecture, okay, Young's modulus and other stuff. Okay, so we talk, you all gave good replies, right? We characterize lots of different densities, right? One common density that we calculate is the bulk density, right? So for any powder, bulk density includes all the void space, or I'm sorry, volumes and all the intergranular void space, right? So if you have two powders, you take the void space and include that in the overall volume calculation, right? So if you include all the void space within the bulk, okay, so the density that we characterize from that is the bulk density, right? Mass of particle plus mass of void plus excuse me, volume of solids and volume of the void space, okay, right? You all would have done, you all know bulk density, right? It's a simple measurement, okay. So from this bulk density, we can get the void fraction, right? So amount of void space within that, bulk powder, right? So void fraction again are the porosity we can calculate from the amount of voids and from the volume of solids, right? So if you just use the volume of volume of voids over the total volume, you get the porosity, right? Or the total pore space or the void fraction within that bulk powder. It's not clear?
Sometimes if your void fraction is given as volume of voids by volume of solids, so volume of voids will into called porosity.
Yeah, so it's a total volume. You just say total volume, volume of voids over total volume.
That's called porosity.
Yeah.
And when its fraction is volume of void by volume of solid.
Yeah.
We'll use that in words. You were saying that porosity and void fraction both are same.
Yeah. So it's porosity. It's usually 100 percentage. It's fraction. So it's in decimals. So void fraction. If you're saying void, it's fraction, right? So it's always in decimal. If you multiply by 100, you get porosity. Okay. It's the same thing. So. Okay, so again using those mass of solids and volume of solids, you can relate to the bulk density and the solid density of the material. Okay, so if you know the void spaces, if you know the bulk density, you can calculate the solid density or vice versa. If you know the solid density and volume of the voids, then you can calculate the bulk density. Okay, so it's again you all would have known, this relationship, right? calculating porosity from bulk density and solid density, right? Very commonly we use, right? Yes or no? Ankur? Yes, okay. Okay, so again, almost the opposite of void fraction is a solid fraction. So, solid fraction is the amount of solid material without counting the void space within the bulk. Okay. Solid fraction, you can see this volume of solids over the total volume. Okay. So, again that will be 1 minus void fraction, right. So, if you remove the void fraction from 1, you get the solid fraction. Right. So, again volume of solids over total volume, almost same relationship you can get if you know the solid density and the bulk density of the material. Okay. And it's also called as, if you see someplace, terminology called relative density, that's the solid fraction is called the relative density, gives the ratio of bulk over true density. Okay, that's called the relative density. Any questions so far? Okay. So, solid fraction, I'm not sure, you might have not studied about packing. Do you study about random packing or packing and probability? Maybe, I don't know if you study, but so in general, the maximum solid fraction for spherical identical sized particles will be about 0.74. That's a maximum packing you can get. But this is a large topic, okay, packing of particles, but I've given one example of how they pack fruits, right. So if it's spherical identical size, the maximum solid fraction you get for spherical particle is 0.74. Again, there are different packing methods that call packing methods, regular Hessian packing, cubic close packing. This is a picture for cubic close packing. Again, when one particle or one spherical particle is touching like 12 other particles, that's like very close packing. Okay. So, if it's very close packing, then you get a maximum solid fraction of 0.74. Okay. And if it's random packing, it will be little less, and then but typical solid fraction for a spherical particle is 0.6. Okay. So, that's what we try to change by compaction process. Okay. So, change the solid fraction by compaction. So, making it closer. Okay. Again, a range of a solid fraction, if it's a fine powder, in general it ranges from 0.2 to 0.5, but if it's compacted powder, usually it ranges from 0.8 to 0.9, okay, in that range. Okay, that means you are removing almost all white spaces within those powders. Okay. Well, this example that I talked about yesterday, Tumsey's talked about Gelisil, right. So, in general their porosity will be higher when compared with aspirin and acetaminophen. Okay, they are like nutrient, sorry, not nutrient, medicine has to be released slowly, right. So, their porosity will be low. Okay. But for Tums or Gelisil, which are immediate release kind of medicines, then their porosity will be little higher, so that the fluids in your stomach can act quickly and then release the nutrients. Okay, so let's do this calculation. Okay, a powder, the true density of about this value is made into cubic compact. Okay, this is cubic 10 by 10 by 5 and has a mass of 0.5 grams. We calculate the bulk density and the void fraction of the compact. So, again make into a cubic compact, okay, and for the same powder you are making into a cylindrical tablet. Okay, you are just changing the shape. Okay, and then how it changes the porosity. So, if you change shape, it can change the porosity, right. It's a simple calculation. So by like kind of this simple calculation, you can see the effect of different particle properties on bulk behavior. If you change the shape, their values change. Same thing, if you change one property, other properties will also change. Anyone did the calculation? So which one will have a higher porosity, cubic compact or a cylindrical compact? Anyone did the calculation? No, not yet. Let me see if I can get the values. Yeah, I should have it somewhere. Got the value? Anyone? No? So what's the porosity? 2? Anyone completed porosity calculation? No? How much? 0.28. Yeah, that's correct. So it's the porosity 28.6 should be. Yeah. So which one has a low porosity, cubic or cylindrical compact? You don't have to do lots of calculations here, okay? So what's the volume of a cube here? What's that? What's the volume of the cube here? 500, right? So what's the volume of a cylinder here? So mass is same, right? So the volume is, for the cylinder, for the volume is low, right? It should be about 420 or something, volume of a cylindrical tablet, okay? So yeah, volume is low, right? So which one will have a lower porosity, cylinder or cube? Cylinder, right? So since again, with the change in shape, you'll change the porosity too, okay? Point 2, yeah. So since that's what you don't have to go until then there, just calculate the volume. From the volume you'll know the volume is low for cylinder than a cube, so the porosity will also be low, right? Okay, so common types of bulk density. So I believe you all talked about this, right? So aerated bulk density, poured bulk density, tapped, compacted, etc. Okay. So can anyone guess what will be the difference between aerated and poured bulk density? I don't know why many are silent today.
Aerated means blowing air for temperature.
What's it?
Aerated means we are using air or any gas.
Okay. Poured means you're just pouring. There will be still air, right? Yeah, it's very close, but but what's the purpose? Purpose of aeration or pouring. Okay, what's the difference? So aerated means again God, you have an answer? No, that's okay. So aerated means again you are aerating it so that you are removing the cohesive bonds between the particles. So they are individual when it fills in the volume or the container. Okay. So there are not any bonding between the particles that affects the bridging when it falls into the container. So for better accurate again characterization. So aerated bulk density again we don't pass air through it. Okay, so specific setup is put in a funnel and make it flow through different slabs, different baffles before it flows into the container which we use for measuring the bulk density. Okay, so when it flows through these baffles, those individual agglomerates or cohesive bonds are broken, and then the particles will be separate when it falls into this container. Okay, so there will not be any bonding between the particles that affects the void or volume calculation. Okay, so again it's common. How many of you measured bulk density in lab? Most of you, right? So you make it flow through a funnel, right? And then it falls into a container and then you get the weight, right? So that's a common. So for grains, larger materials, we will not use this kind of baffle assembly, but it's most commonly used for small fine powders. Okay. Bulk density, you might know, depends on the height at which it flows down to, right? If it's too high, then there will be chances of fluidization and you might be losing some powder. But if it's too low height, then again still there will be some agglomerates that will contain some bonding between the particles that affect the volume calculation. Tapped bulk density, again, you all know tapped bulk density, right? So you tap it for some amount of time and then again you calculate the change in volume after tapping. Okay. So one of the major challenge will be again how many number of taps you can do. You don't know, right? So sometimes with the number of taps, the volume keeps on changing. But there are many standards to give an optimum number of taps you have to do. Okay. How many of you measured tap density? So for agriculture students, it's very similar. Like you put sample in a powder, in a container, and then tap it like this. Keep on tapping. The volume keeps on changing. Okay, it's very very similar. If you're loading lots of material in a truck or container, when it reaches its destination, usually the volume goes down, right? Due to tapping, small particles will fill into the large, void spaces and the volume goes down. Right? That's what we will be quantifying using tap density. Okay. So again, we'll not know how many amount of, taps, but there are, studies and there are equations that gives, that helps us calculating the number of taps that needed. Or you can, if you wanted to characterize, you yourself can do some experiments and get the trial and error and get the optimum number of taps. Right? So common is one sample instrument, but for grains and large materials, there are large cylinders that allows us to tap in a big volume of powder. You load the samples in cylinders and then you fix the number of taps you wanted to tap and then get the change in volume and get the tap density. Okay. Any questions? These are simple measurements, right? So you both are smiling. No, you can still smile, that's okay. It's okay to smile. Okay. Okay, so we'll talk about compressibility. Okay. Compressibility and compacted bulk density. Okay. So before going into it, again, it's very related to the bulk tap density. Okay. This, this equation you might see in powder papers a lot, Kawakita and Lude paper. So they related the number of, taps and their change in properties, that's related to their flow behavior, their cohesion, etc. Okay. So this N here is the number of tapping, C is the compressibility or compactability of the sample. So that's calculated from the tap density and the bulk density of the samples. Okay. So if you know the tap density, bulk density, so you can get almost, I'll talk about this N and these constants. You can, little bit know about their flow properties and their compressibility. Okay. So again, constant A is related to compactability, how much the powder compacts when you tap, and then again it's very, related to the Carr's index. 1 over B, this constant is related to powder's cohesion and its flow behavior. Okay. So again, smaller values in general for A and 1 over B, it shows a better flow behavior. Okay. So again, number of taps, tends to infinity means again, you can go on increasing the number of taps, to get the tap bulk density, right? But at one point, it kind of stabilizes, becomes constant. Okay. So again, this is a simple relationship, right? So if you plot N over C over N, versus N, you get a very, linear relationship here. Tapping number, the ratio of tapping number over compactability or compressibility. Okay. So from these lines, you get the slope and intercept that gives the constants A and 1 over B. Okay. So again, simple relationship, simple constants that can get you the get you more understanding about the powder bulk behavior. Okay. Are you still here? Okay. Yeah, go ahead. Oh, what is that? So y is number of taps over compressibility or compactability, C. X is just number of taps, N. N over C. Okay. So again, these are some examples from, Kawakita and Lude's paper. So you see there's almost, the values are not constant. Some papers will some, samples will have high N 1 over B values again, as we saw in the last slide. So lower values indicates better flow properties, right? Talc, all know talc, right? Usually their values are, the particle sizes are small, so their, flow behavior will also be poor. Okay. But again, if you compare sugar and granular sugar, the values are close, but you can see the difference in A and 1 over B values. So A value is much smaller than, the granulated sugar, the A value is much smaller than regular sugar. So granulated sugar is larger size, right? So their flow behavior will be better than, small sized sugar powder. Okay. Again, there are, if you go into literature search, you will get lots of, lots of values for different powders. Okay. Again, porosity increases with decreasing particle size. Right. Again, we'll come back to that. Come back to that Kawakita and Lude, and also the Hausner ratio and other things. When we talk about flow behavior of the powders too. Okay. So how does porosity, increases with decreasing particle size? So mainly the particles are cohesive. If there are some cohesive, forces between the particles, then they try to form clumping or bridging between those particles. That leads to increased porosity. Okay. But if it's larger size particles, you might know if it's large size particles, their porosity is always high, right? But again, if it's for size powder, smaller size, uniform shape, uniform size powder, to reduce the particle size, in general, if it's cohesive, their porosity will also go up, right? Mainly due to cohesive bonding between the particles that forms arches when you are pouring into bulk. Okay. Similar, moisture content, if you increase the moisture content, it reduces the porosity, right? So when moisture, if you increase the moisture content, water content will fill in the void spaces and pore spaces, and then, reduces the overall pore space or void spaces, right? So again, I'm just showing some, picture of small particles here. If you are increasing the water content, water fills into the void space and reduces the porosity of the particle or powder. Very similar, if surface roughness increases, porosity increases, right? So if it's very rough, there will be more mechanical interlocking between the particles. Okay. So if there is high mechanical interlocking, then the porosity will also go up. Okay. As you can see from small, again, picture here. It's higher mechanical interlocking from larger friction between those particles and forms into smaller arches and stuff, at bulk level. And this graph shows here, if the coefficient of roughness increases, the void fraction also, increase. Okay. Too much theory, or is it okay?
Roughness can you explain?
What's that?
Roughness.
Hmm.
How it is called that increase or porosity increase?
Okay, so if the roughness is high, you can, simple example will be, if you take some fiber material, they will be rougher, right? But their porosity will also be high, right? Because if you, heap some straw, usually what will happen, they interlock, right? Interlock and form into heaps, and there will be lots of white spaces inside, right? So that's what, this picture indicates. If it's highly rough, then there will be higher friction between those particles, and then they form into arches. Okay. Any questions before we go into compacted bulk density? No questions? Okay, I'll go back to one, example here. So it says, with, it's correlated, this Kawakita and Ludde Fastener ratio to, it says that, with number of tapping, the change in density will indicate flow behavior, right? Right? With increased number of tapping, the change in powder property, when it changes volume during tapping, it indicates a flow behavior, right? You understood, right? Right? Is it clear? So what could be one major disadvantage of using this method to understand the flow behavior? Where do you see very close, where do you see incompressible flows? At least in solids, not in fluids, but in solids. Like bulk powder flow. It's not about density. Any thoughts? But it's, again, we'll talk about that in a minute. Whoever gives an answer in next 1 minute will get a chocolate. You'll have to think more. It's not a straightforward answer, but we'll talk about that in the Hausner ratio lecture too. Okay. Any thoughts? Go ahead. You have. Go ahead. Yeah. So it's, we are relating here number of tapping, same like Hausner ratio, change in tap density to flow, right? Flow behavior. So if the tap density is not changing, if the density remains same after tapping, it will indicate better flow, right? Right? That's what they say. If the density is changing a lot, that indicates powder compressibility, right? Higher compressibility, that shows the powders will have poor flow behavior, right? But what will be one major problem with using that approach? Can we use that for all powders? We just talked about irregular shaped particles, right? I will give the answer, okay, but we will talk about that later too. So what happens, for example, if it's a very highly cohesive powder, for example, high moisture fruit powder, okay, the moisture content is like 30-40%, okay. When you tap, what happens? It doesn't change in volume, right? It remains the same. But does that mean it's a good flow behavior? It's not, right? So that's one challenge, So we cannot use that approach blanketly for all, for all powders. Same for highly irregular shaped powders. That might flow very well, okay. Since they are highly irregular, they form some interlocking, and then when you tape, the volume will change a lot. That will indicate it is having poor flow behavior, but in actual they will have better flow behavior, okay. So when why I'm saying this is, when you are evaluating powder, okay, just don't depend on the data that you are getting by different approaches. Make sure to understand your powder or characterize them very well, so then you can get meaningful inferences on their behavior, okay. Just as an example, I said, if it's very cohesive and you are using Hausner ratio to get the flow, and you might write, okay, it's flow, it flows very well, but actually it's not, right? So someone would come back and say, no, this powder doesn't flow well, check back your values and stuff. So make sure to read through your data, think through your data when you are writing your thesis or publishing papers. Okay, just some more suggestions, but we'll talk more about specific example in the flow lecture too. So we'll talk about compacted bulk density again. I'm just giving an example of grain bin. Not sure. I know it's not very common here, right? Grain silos, but still it's coming up in, at least in Punjab and some parts of India, or see lots of huge grains. So you'll see when you are loading samples in large containers, it could be a grain silo, or it could be a truck, or it could be a container. What happens, due to the weight of the sample above, it kind of compresses, right? So compresses the sample, and the density is also changing, right? So the powder may not have, or the bulk material may not have the same density at the top and the bottom. So the bottom, the density might be high, the top, the density might be low, okay. So that's that's what we characterize from using compacted bulk density, and also for making tablets, compacts, etc. We use this approach, okay. So at least for grain bins or large silos, why do we have to worry about this change in density? Any thoughts? What's that? Yeah, aeration, one good, that's a good answer. Aeration will change. If the density is high, the aeration will be poor. Go ahead. Yeah. Stability, not directly, maybe, yeah. It's not, it's a good answer too, but usually not, okay. So it's bulk density, right? We're talking about bulk density, right? So what do we use bulk density for mainly? What do we use bulk density value for mainly? What do we have to measure for any material? Why do we have to measure bulk density? God, keep on. My question might not be clear, but still, based on your responses, I can modify the question. So, what is the basic purpose of bulk density? At least for when you're manufacturing food powders. Packaging, exactly. So, how much material you can fill in a container or in a packet, etc. Right. So, the most property that's important is bulk density, right? How much you can fill in container. So, it's the same thing for large storage structures too. So, based on the density, you are changing the amount of materials, right? I'll give one example. So when they store these large amount of materials, usually they take insurance for those bins or whatever materials, right? So that they don't lose money if something happens. For example, if the bin breaks or bin fails, they most common, it's big industries here also, I think, will do insure their saved material. So if it fails, for example, how does the insurance company know how much material was there, right? They do not know, right? So if yes, they can roughly estimate based on the volume of the container, right? But from the volume of the container, you can estimate amount of material present in there by using bulk density. But in actual, with compacted bulk density, there might be more material than the actual volume of material, right? So that's again one common place, at least in food and grain, where we use to get the actual volume of material, due to this change in density that we use for calculating, for multiple purposes. Okay. Same thing for shipping too. Inventory. For inventory calculations, how much material you have in the bin. So you'll have to use the compacted bulk density. So at least in the US and Canada, they use a term called pack factor. How much material is packing for grains, okay, at least for grains. How much is packed at the bottom? There are different constants for different grains by which they use to calculate the amount of material within the bin. Okay, again, that's one.
Any effect of weather in bulk density?
Whether definitely if you have higher moisture, then definitely the density will change, right?
Which been higher or upper portion or lower portion?
Okay,
Where
that's
you talking about a bean?
wherever the moisture is absorbed. Okay, that's a good question, but you'll have to take my grain drying and storage class that I teach in 2026 spring at Purdue. Okay. No, that depends on the conditions outside. That there are multiple factors go into play depending on the season. Okay, it can absorb in the top or in the bottom too. Okay, but we can let's say another subject like aeration. You told aeration, right? It's highly related to aeration of grain bins. Okay. So again, compacted bulk density. So how do we calculate is by uniaxial compression, one-dimensional compression. So you put samples in a container and then just compact in one direction. Okay, you control the forces on all the other three sides and get just apply force from the top. Okay. And these are for generally for powders, typical 70 or 75 mm ring diameter are common to get the compacts or compact densities, and again it can vary too, but these are common sizes for powders. One of the challenge will be, again, there will be wall friction, right, when you're compacting. That might affect your calculation of density. So you'll have to make sure that there is no friction on the walls that affects the compaction of the powder. Okay, commonly used, what do you call? I forgot the name. Starts with G. It's a not glass, lubricant. So you apply on, huh? Huh? What is it? Glycerine, maybe? Yeah. Is that glycerine? Yeah, it starts with G. Maybe glycerine, it might be wrong. It might be right. Okay. So, some lubricant or low friction liners, there are like wax papers. We commonly use wax sheets, put it on the side and then compact so the friction is low. Oh, it's from the back. No. Someone had a question? No. Oh, grease use. Grease, okay. Grease, they become very sticky. Glycerin, I think glycerin is common, it's not very sticky. Or, most commonly, you use powders, like, very common is magnesium stearate. It's a powder. So what they do is compact with magnesium stearate first. So it kinds of softens the wall and smoothens the wall. And then remove the magnesium stearate compact and then you put the actual powder and compact. Then, it will be very friction. Again, make sure you are using length diameter ratio of less than 1 so you can get the bulk density at different compaction pressures. Okay. So you can correlate with the pressure or the amount of material at different heights within a large silo structure. Right. You all would have learned about pressure, right? Compaction pressure, calculation of pressure at in bins and silos. You remember the equation name? What's that? Those are for stresses, right? For calculating pressure at different heights. Yeah, Jansen's equation, right? So that's very commonly used, right? No? I don't. What? Can you repeat it? Grain? Okay. Is it used for solids, powders? Huh? Grain structures? So what do they calculate? Lateral pressure? Okay. 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 Yeah, we usually, I don't know, I commonly use Jansen's theory. Yeah, I don't. Okay. Yeah. Jansen's theory. Yeah. Powders also Jansen's theory is common. So I never use. Maybe I should check that out. Okay. So which textbook it has? Okay. Okay. Oh, okay. Sahan Singh book. Okay. 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 I will check that out. Okay. So again, there are different, compaction equations that you can use for relating the powder properties, change in properties. You don't have to worry about these again. Based on change in stress, you get the density of the powders. Okay. So at different stress values, you get the density. Again, there are tons of equations, but most common ones. We'll talk about Haeckel relationship. Kawakita. I'm not sure you would have learned about Jennings. Jennings and Johansen. Jennings. They have different papers, but Jennings and Johansen theory is very common when it comes to bulk solids, storage and handling. Okay. Again, so some of the best fitting models for compaction of powders that that relate stress and the bulk density. Again, Johansen is very common. Again, Jennings at very large stress values. So if the silos are tall, then you can use this Jennings relationship. Okay. Again, those are again simple relationship based on the change in density over stress values. Okay. So what happens during compacted bulk density? Again, I'm showing for one granular one material, but in bulk also it happens. So when you increase the pressure, the volume is also changing, right? The overall volume is changing, right? So there will be, you might have learned about, right, elastic deformation, plastic deformation, etc., right? So initially it goes through the elastic deformation. So when it exceeds the yield point, then you will get the plastic deformation. right? So the particle starts breaking, and then there will be the broken particle will fill into the void spaces and then make those dense compacts. Okay. So during compaction, again you can calculate the specific volume. That's called Walker equation, very highly used by pharmaceutical industry for when they make tablets, etc. Okay, compacts, tablets. Okay. Again, it's again the logarithmic model gives a simple relationship of change in volume. Again, it depicts the change in plasticity and elasticity of the powder, or plastic deformation and elastic deformation of the powder, and how it relates to change in volume when you are compressing the powders. Okay. So again, there will be sudden change in volume when there is too much, a high level of plastic deformation. Okay. Then again, the volume will not change until it reaches the final maximum density. Okay. Again, Walker equation that relates the change in volume to the applied pressure. Okay. So if you know the applied pressure, if you know the volume at different pressures, so you can calculate the volume at zero pressure. Second, volume at interparticle pressure is zero. Again, it's very similar like the other relationship that we talked about, this equation that we talked about. So in extra zero might give you wrong values. Okay, because actual conditions you might not see an interparticle pressure of zero, right? So there will be always some pressure between the particles from cohesion and addition between the particles, right? So that's why you might get some error in the values. So again, just for summary, if you know the amount of white space in the powders or amount of actual solids in the powder, you can get the white fraction, solid fraction, etc. Again, all those other properties like shape, size, surface thickness, etc. will also influence the density and the porosity of the material. Okay. Any questions? I'm not going to read everything, but any questions? So the lambda is the fitting constant, but that can do again the porosity. Okay. So lambda is the fitting constant from the equation, or the slope, intercept and slope. That's very similar to what we talked about in Spriggs equation. So V0 will be the intercept at zero volume, and then you get a lambda from the slope. Okay. So lambda, I didn't include all those things. So lambda will be highly useful when you are compacting powders, especially making tablets. Okay. So what will be the change in compacted powder when you change strain rates, for example? Okay. So all those information, strain rates, properties, etc. We can get lots of information from this change in lambda value. Right. And if you go, it's mostly used in pharma industry, but not much in food, unless you're compacting food powders. Okay. Any other questions? No. No question. So we talked about compacted bulk density, right? So before that, what time tea comes, Prakash? 11:15. You just seeing the clock and saying, 11:15, just randomly, no? Okay, that's okay. Okay, 5 minutes, okay. We'll talk about talked about compacted bulk density, right? So you know where we apply, right? So why do we apply bulk density? Why we need to know, right? Where it's useful, right? And where we use tap density, right? Mostly for shipping, packing, etc., right? So why do we care about the void fraction or the solid fraction. Any examples of application? What do we have to quantify void fraction? Not what, let me rephrase my question. So, any application where you want to know the void fraction within bulk powders? Any example application? Don't talk about, shipping and handling. Okay, we already done with that. Any other examples that you can think of, where you will want to know, you should know the void fraction of the bulk powders. What is that? Yeah, so dissolution rate, right? So one common is dissolution rate. So if you know if its void space is high, then the dissolution will be higher, right? Any other examples? So did I go very fast, or is that okay pace, or is it very slow? How many of you think I went very slow? And I'm not your teacher, so you can be free and frank with me, okay? So that I can change for the other lectures, right? Yeah, sure. Hold on. Before that, I'll come back to that. So one common application of why we want to care about void fraction is agglomeration again. So when you are agglomerating any type of powder, again, same thing we talked about binder load, right? Yesterday, how much binder you want to add. So this void fraction will influence the load of binder that you wanted to add during agglomeration process, so that you get good granules. Okay, so yeah, we'll come back to your question. Aerated bulk density and usually not, aerated bulk density is almost, the purpose here, aerated bulk density, is just to break the individual particle bond and make them individual when they flow into the cup during measuring bulk density, right? But you can apply, how much aerated bulk density, as said, maybe, yeah, it should be. Yeah. Hmm. Oh, okay. So for that, more than aerated bulk density, your particle density will be much better. So that will give, a cleaner separation. So get the, particle density. For example, fibers particle density will be much different than protein particle density. So bulk may not give a cleaner separation. So you might, I'm not sure if you remember that Geldart chart, they usually use that particle density to classify their fluidization behavior. Okay. For air classification, so particle density will be the one that will give you more information for separation of particles. So very simple, you would have known, you would have seen those winnowing machine, right? Screen cleaners that are used to separate grains from chaff. Yeah. So it's the same principle, air classification, right? So we use density, particle density of grains and the chaff to separate them into two streams. Okay. So it's almost the same principle, right? But here the particle sizes are very small. So yeah. Yeah. So that will be difficult. Any other questions?